Hi everybody. Maybe you're one of the very few people on the planet who has an original AA3000 motherboard. Yes, the prototype that Commodore created but never went on to commercialize. But perhaps more likely you are an owner of one of these motherboards, the AA3000 Plus, a more modern recreation that sticks close to that AA3000 prototype. Either way, if you're lucky enough to have one of these, then it contains an additional chip that no other Amiga has, the DSP3210. What is that? Well, it's a digital signal processing chip that executes instructions entirely independently to the CPU. It has DMA access to RAM, so can operate completely without the CPU's intervention. Inside it, it's a pretty powerful architecture for its time, being fully 32-bit, meaning that it can execute 12.5 million floating point instructions per second, which gives it some pretty unique capabilities. Put that inside a regular A3000 and what can you do with it? Well, I've done a bit of programming of this chip and these are the results. First of all, you could calculate Mandelbrot's reasonably quickly, even with a 68030 onboard CPU, something that would have been entirely impossible for an A3000 back in the day. Additionally, because 3D graphics require a lot of floating point manipulations, you can also write a 3D program for the DSP chip alongside the 030, and in this case wrap it up in a demo. So all in all, the DSP chip is a very capable addition to an Amiga, but I have been asked the question a number of times, how do I program the DSP3210 if I want to create my own programs? In this video I'm going to explain how. I'm going to walk you through what exactly you've got to do to program that chip up. And to structure what I am talking about, I've broken things down into a number of sections. First of all, I'm going to give a brief overview of the architecture and how the DSP integrates into the Amiga architecture. Then we'll talk about registers, addressing modes, and the instruction set for the DSP. Third part is about starting and running the DSP. Then a little bit about program design. What programs are going to make the most out of that DSP? How do we bring it all together though? How do we integrate that CPU program with the DSP program, and most importantly, turn it into an executable? So let's begin with an overview of the basic architecture. The AA3000 and the Plus version are both based on the A3000's motherboard. And the A3000 itself is based around the Motorola 68030 CPU chip that I'm visualizing on this slide. And that chip, along with the rest of the 68000 series of processors, can access the full 4 GB memory map. In other words, the full 32-bit address range is available to the CPU for access. It doesn't matter what the location is, it will be able to access it. Now, I know on the Amiga range not all of that is devoted to RAM. Some areas of it will be instead memory mapped I/O, and other areas are devoted to the custom chipset. But for these purposes, let's just think of that entire 32-bit range together. So that's the CPU. Of course, on the motherboards we're talking about here, we have a second processing unit, the DSP3220. So what about it and its addressing capabilities? Well, the good news is they're exactly the same as the CPU. The DSP chip can access just as easily the full 32-bit address range as the 68030 itself. There are no limitations. And that opens up a lot of flexibility for how we use this DSP chip. It doesn't matter where the programs and data are in memory, it can access them. Additionally, there are some direct controls between our CPU and our DSP. In fact, each can interrupt the other, and I'll come on to talk about how that's done later on. There is one special thing about the memory architecture as far as the DSP is concerned, though. There is one small segment of memory at that hex address there on the slide that is onboard RAM. There is only 8 kilobytes of it, not very much out of the full 4 gigabyte range, but that is onboard RAM. Obviously the 68000 series CPU cannot access that onboard RAM directly. It's only visible to our DSP chip. But into that onboard RAM we can transfer the code we want the DSP to run, and or some data as well. And the reason for doing that is simply fast access. Again, I'll come back to that more later on. And one final thing about architecture before we move on: do not attempt to write a program that uses the onboard SCSI operated by Super DMAC chip at the same time as the DSP. The fact is that there is a hardware fault in the design of the logic around the DSP that will cause the Amiga to crash at some point if you try and use both functions at the same time. So simply don't do it. We don't want to corrupt anyone's SCSI files. But let's dig a little bit further now into the DSP's registers, its addressing modes, and its instruction set. Really, to know about this subject, you have to open up the information manual. That's the front cover there on the left. It's hundreds of pages long, and it is available from my GitHub site that you can see the address of there. If you want to know more about the DSP chip, there is really no substitute for downloading a copy of that and studying it at length. Almost all the information in this video is formed from reading the information manual. But at an overview level, let's walk through what registers we got available to us and then the instruction set. So to begin with, we have registers R0 to R22, which are full 32-bit wide integer registers. As we'll see in a moment, they are used for integer arithmetic and also as pointers into memory. Next, we have A0 to A3, which are single precision floating point registers, sometimes called the accumulators, 4 of those. And finally, there are some I/O registers that control the operation of the DSP chip. I'm not going to talk about those in great detail here, but they are covered in detail in the instruction manual. If you need to know more, that's the place to go. But looking a little bit further at those R registers, the integer registers, there are some things to know about them. First of all, R0 is hard-coded always to be the value 0. It enables move operations to actually be encoded as add operations. Registers R20 to R22 do have some internal uses, so although in principle they're usable by programs, in practice they are off limits. And then finally, for instructions that affect the accumulators A0 to A3, there is a dividing line between the remaining R registers. R1 to 14 can act as pointers into memory, whereas R15 to 19 are index registers, and we'll see the use of that in an example in a minute. What about addressing modes? Well, first of all, data sizes. Through the instructions, we can access a byte, in other words, 8 bits, a short, which is 2 bytes, and a long, that's 4 bytes. So the same kinds of data sizes that you have for the 68000 series CPUs, albeit with perhaps slightly different names. We're using the name here short rather than word. And the way to address different data sizes is part of the instruction syntax, but long is always the default. So if there's no data size given, the instruction is doing a long access. The way to access memory is using the star operator, which is just like you do in C. So there's the example, R1 equals star R2. So in other words, set register 1 to be the contents of the memory location that's given by register R2. And of course, we can load accumulator registers from memory in just the same way that we can load the R register. So there's a second example there where we're loading A0 with the contents pointed to by R2. All very intuitive. And of course, these are memory reads. You could do memory writes as well using the similar syntax. There's also addressing modes for post increment and post decrement. So here we're not just loading R1 from the location pointed to by R2, but we are then incrementing the pointer R2 here because the data size is applied by default to be a long. We add 4 bytes to the register R2 to point to the next long through the post increment, and post decrement is simply a minus minus after the register name instead of a plus plus. There are no pre-increment and pre-decrement addressing modes, by the way, if you are expecting to see those. And finally, an index mode that we don't see on the 68030, and that is indexing via another register. So here, first of all, let's assume that register R17 is set to the value of 16, and then look at the next instruction. We're loading the register R1 with the contents pointed to by register R2. Once that's complete, we're then indexing R2 by whatever the value of R17 was. Well, it's 16, so we're going to add 16 bytes onto R2 once that memory access is complete. So this gives really quite a lot of power for accessing table-like structures within memory via the register indexing. And of course, the register index could be negative as well as positive. Now, I'm only going to cover the instruction set at a pretty high level here, many more details in the manual. But as you would expect, there are assign functions, so you can assign an integer to an R register. You can move from one R register to another, or a R register to or from memory, as we've just seen, or to and from an IO register. We've also got a full range of logic instructions, adding, subtracting, and or not, exclusive or, etc., etc. There are others as well, and shifts are also built into the instruction set, whether that's arithmetic or logical shifts, left or right, and also rotates left and right. What there isn't, however, are specific bit field instructions. If you want to access particular bits within a byte or a short or a long, then you need to use the logic instructions and apply a mask. Those were the integer instructions. What about the floating point register instructions? Well, there are several of these, so it's going to take up a bit of time to cover them. So first of all, as we've already seen in one of the examples I gave earlier, you can move to an A register from memory, or the other way round, to memory from an A register. And then there are also multiple combinations of floating point multiply, add, and store instructions. And they are typically of the form shown there on the slide. So let me begin, but perhaps on the right of this equation, on the far right. So we could take an A register or a memory location, the contents of it, and multiply by another A register or memory contents, and then either add or subtract that from the positive or negative value of a further A register or contents of memory location, then assign that to an A register and possibly also store that in memory as well, optionally if we wish. So that's really a pretty complicated multiply and add and store instruction that you could do an awful lot with in a single instruction. Additionally, there are a number of so-called special floating point instructions of various different types. So you could convert between the more regular and certainly standard on the 68000 series CPU IEE floating point format into the internal DSP floating point format. So that's an essential step when you are taking floating point values between the CPU and the DSP. There are instructions to convert floating point values to or from 16 or 32-bit integers. You can round floating points to the nearest integer, and you can conditionally move and store a float, so move to an A register, and if you wish to, store that in memory based on certain conditions. And finally, a seed for division. So division isn't natively built into the instruction set for the DSP, but you can calculate a division by using the seed function first to get a rough approximation to what the answer is, and then refining that using the Newton-Raphson method to gradually improve your answer for division. So that was integer and floating point register instructions. What about all the other instructions we need? Well, let's run through those briefly. So as you'd expect, you've got both conditional and unconditional go-to instructions, and a conditional go-to variation where it's for looping. So an R register counter is decremented through each loop. We've also got instructions to call subroutines and return from them, and then into something quite interesting, which is do loops, two varieties of those. Now, the syntax for these involves determining and describing the number of instructions that you want to loop, and it's always one more instruction than is stated, n+1, and then the number of times you loop, either a fixed number, n+1 times, or based off a register. Again, one more than the contents of the register. We've also got instructions to wait for an interrupt and then return from the interrupt routine, and not surprisingly a NOP, a no operation instruction. So that's an awful lot to take in. Let me walk you through a very brief example, albeit one that is pretty complicated. Just 2 lines to it, so let's work through those. So the first line, do 0, R3. In other words, do the next one instruction, the number of times that is in register 3 plus 1. So if register R3 contains 4, then we're going to repeat the second line that we can see there 5 times. And what is that second instruction? Well, let's walk through that. I think the place to start might be working from right to left here. So on the far right hand side we have star R1 plus R17. In other words, take the contents of the memory location pointed to by R1, and once you've done that, post increment R1 by whatever R17 is. Once you've determined what the contents of that memory location is, multiply by whatever is in accumulator register A1, and subtract that from the negative of whatever is in accumulator register A0. Once you've determined all of that, update register A1 with the result, and also place that result into the memory location pointed to by register R2, and post increment that register by the contents of R16. Well, that was quite a mouthful to go through, but I think it demonstrates exactly how powerful some of these instructions can become and how much you can do in a relatively brief number of instructions, just 2 in this case, doing a pretty complicated floating point calculation there. So how do you actually start the DSP the very first time once the machine has powered up? And then once you've done that, how do you get it running on a regular basis? Let's work through that. Well, the first thing to go through is that there is a new control register that is in the custom chip space of the memory map. Now, the location of this control register depends on whether you are reading it or writing it. So the read location is in hex DD005C, and to write to it is again in hex DD0080. And because of the odd way that the logic for the DSP is set up, you read it as a long and write to it as a byte. Now, why is it like that? Well, remember, this is all based on a prototype machine that Commodore never finished, so that's why there are these odd sizings going on. But there's a further caveat. There's no point in trying to read the control register, certainly on using a Super DMAC version 2, because it simply doesn't work. The DMAC version 2 isn't set up to be able to store the control register bits that we'll come on to in a moment. So really, reading is a bit of a red herring. All we could do is write to this control register and know that it's working properly. So what are the bit allocations? Let's start at the top and work downwards. Bit 7, if you take that bit low, it resets the DSP. We're coming back to that very shortly. Bit 6 isn't used, so we can ignore it. Bits 5 and 4 enable the DSP to interrupt the CPU either at interrupt level 6 or level 2 if those bits are taken high. That looks extremely handy, and it is, but let me just say one other thing, which is on these motherboards, and I think this is true for all versions of the AA3000 Plus, the interrupt level 6 line is not connected to the CPU accelerator slot. So it may well be that the DSP in your program triggers an interrupt 6, but the CPU, if it's running off an accelerator, won't see that because the signal isn't connected. Whereas if you're running with the onboard 68030, that is connected. So the sum total of that is best not to use interrupt level 6 in your programs. If you really need to use interrupts and interrupt the 68000 series CPU, then use level 2. Back to bits 3 and 2 now. Well, they're read-only, so not that useful, but in principle you can read whether the DSP is trying to signal an interrupt, although the way to use that, if it worked, would be in your interrupt server or interrupt handler software to just check whether it's the DSP that's doing the signaling or some other hardware. Finally, we've got bits 1 and 0, which are extremely useful and important. They allow the CPU to interrupt the DSP. And here, the DSP interrupt level 0 is higher priority than level 1. They're active low. And in a moment, we'll see how to use some of these signals in order to get this DSP going. So how do we start the DSP? Well, we start with triggering a reset. So we write 7F followed by FF to the control register. That takes that bit 7 low and the DSP goes into reset. When it goes into reset and comes out of it, what it does is start executing its own internal boot ROM, which will take it a few cycles, and then it will sit there waiting for an interrupt. So from the programming side, we do need to give it a moment or two just to go through that process. In the meantime, What we need to do is to write into location 0, yep, writing into location 0 in the lowest part of memory, the location of where we preloaded the code we want the DSP to run. Then when we're ready, we trigger interrupt 1 on the DSP by writing FD to the control register. That takes the necessary bit low, which triggers the interrupt. At that point, the DSP sparks into life. It reads in the code start location from where we previously saved it, and then overwrites the value in location 0 back to 0. So that becomes a flag for knowing that the DSP is active and doing something. And then the DSP begins code execution, and off it goes. Now, what happens next depends on what you've coded, but typically what I do in my programs is to then relocate the DSP code that's critical to whatever our application is into its own onboard RAM space. That, of course, necessitates writing position-independent code because we're moving from one place to another. And then what I typically do is once that relocation is done and we're operating out of onboard RAM, is simply for the DSP to sit there and wait for an interrupt, allowing our CPU to set up the rest of the program and the initial data that we're wanting the DSP to act on. Therefore, the way things are set up, that means that we still have our copy of the original DSP code sitting in the shared memory space, and that is the place to keep the shared data. In other words, the data that is going to be used by both the CPU and the DSP. They can both see that data, so to speak. Whereas, recall, the CPU cannot see the onboard RAM of the DSP. So that shared data area becomes really important. That's where the CPU is going to place all the information the DSP needs to operate, even if the DSP then goes and copies that internally and acts on it. So once the CPU set everything up, what do? Well, we're going to trigger int1 again in order to get the DSP going. And from that point, the DSP is going to go off and do whatever you programmed it to do. Potentially that will see the application through to the end if you never need to stop the DSP again, or perhaps, as is often the case in my programs, it will carry out some functions and then wait again for a further interrupt from the CPU when the next chunk of data is ready, and so on and so forth. It's also possible to write programs the other way round, so to speak, so that the DSP is always operating, and when it's ready for more data, then it interrupts the CPU. As I say, do that through interrupt level 2 on the CPU to ensure that it works, and then the CPU can go through its own interrupt routine to supply more data to the DSP. That's certainly an alternate coding model. So having been through all that, where does that leave us on program design? Well, I think there are a few considerations to take into account. The DSP strength is in doing floating point calculations. Really, there's no point in trying to challenge it with integer arithmetic. It's not particularly strong at that because it cannot do integer multiply and integer divide in the same way that the CPU can. So perhaps stick to applications that need a lot of floating point. Having said that, it can only do adds and subtracts and multiplies natively. Divide is possible, as I've explained earlier, but it does take a few cycles. So it's certainly feasible to do division on chip, but anything more complicated than that is probably best via a lookup table. When you put it all together, tasks that require heavy floating point calculations are going to be the ones that work the best, just like the Mandelbrots. But what else though? Well, we need to think about how this whole architecture hangs together. The CPU and DSP share the same address and data buses as we've just seen at the start. That means that they both can't access it at once. They have to take it in turns. So to the extent we can manage it, it would be good if we can have the two different processors accessing memory at different times. Secondly, the DSP can access its local onboard RAM 3 to 4 times faster than fast RAM. I know this because I've done some tests on it. Really, the DSP access to memory on the motherboard and also to any memory on CPU accelerators is a good deal slower than the local RAM that the DSP has on board. That's the reason for trying to make the most out of that 8K window that we have available to us. Another thing to bear in mind here, therefore, is the opposite of that, which is if there is an accelerator on the machine with onboard local RAM on the accelerator, the CPU is likely to be able to access that just as fast as the DSP can access its own 8K of local RAM. And so if you've got an accelerator in the card, in the machine, you need to think really hard about how your application is going to work. That makes it sensible to use the DSP instead of the more simple thing of just relying on the CPU. And that's particularly true if you've got a 68060 accelerator in your system. The FPU there is broadly the same speed as the DSP chip for doing floating point calculations. So if you're writing for the 060, you may consider that actually worrying about the DSP is unnecessary. So where do we get to with all of this? The longer that the DSP can operate out of its local RAM, whether that's the instructions for it to run or the data that it's acting on, the better. And therefore, the less the DSP has to access fast RAM, the better too. The more it can stay in its local RAM, the faster your application will be. So if you put that lot together, where do you get to? Well, what I have found to work well is what I would call a tick-tock route to tasks. And that's basically to break tasks down into two parts, A and B, and to have the CPU, and the DSP working on those two parts independently. So say the CPU is working on part A and the DSP on part B, and when they're both ready, they swap roles. And that keeps them working on different data sets, although working simultaneously. What does that look like in practice? Well, here's the example from the what might have been demo. So at the top there, we've got the DSP, which is building the image in the first chunky buffer to build up the 3D image. At the same time, the CPU is acting on the second chunky buffer to do a chunky to planar conversion into our second planar set of memory there ready for display. But all the while this is going on, what the user is seeing is the first planar bitmaps. So the user doesn't see any of the calculations going on. Once all those different tasks complete by both the DSP and the CPU, they could swap over. The DSP creates the next frame in the second chunky buffer, while the CPU is doing chunky to planar on the first chunky buffer. And in the meantime, the user is looking at the second planar buffer. So what we've got here is the DSP and CPU always working on different areas of memory, and the user always seeing something that is double buffered. The Mandelbrot program works in a very similar way. Okay, it's not doing chunky to planar and 3D graphics, but what's happening there is that the DSP is working on one column of the screen display for itself, while the CPU is drawing the results from the previous column into the screen buffer. And then when they're both complete, they both move on a row. So the DSP is always one column ahead of the CPU. Again, that way they're both operating on different data simultaneously, and we get the best performance. So that's an awful lot of information. But here is the question that you've really been waiting for, which is how on earth do you bring that all together into a single executable? Well, let's think about our project like this. On the left there, we've got multiple perhaps C or assembly language source files. If that was the entirety of our project, we'd know how to compile that and produce an executable. So that isn't where the problems lie. But in this particular case, not only have we got those 68K source files, we've also got some assembly language DSP routines that we need to integrate. And the question is, how do we bring that all together to produce an Amiga executable? Well, let's look at the programs we can use, first of all, to create our binaries. So on the left, the 68000 series C and assembly language can be compiled or assembled using VBCC and VASM. We'll come back in a minute to why I'm particularly specifying those programs for compilation and assembly. But what about the assembly language for the DSP? Well, I've written an assembler for the DSP chip. It is relatively basic, but it's enough to get the job done. It's called DSP3210 and it's available on AmiNet. So that's the place to get the assembler for the DSP chip. Like VBCC and VASM, it runs in Linux type settings. So if you're a Windows user, you can run it, for example, under Cygwin, or you can run it under a native Linux distro. So that solves the issue of assembly, but still doesn't help us with creating that Amiga executable. And when we start thinking about that, we uncover a problem. The issue is, if we want to write a program of any complexity, then we want to be able to share symbols between the two sides of the equation. We want to be able to share symbols between the CPU side, the 68000 series side, and the DSP side. We don't want to have to work out offsets into the DSP program and hard code them in, nor do we want to have to work out offsets into perhaps a data space on the CPU side and hard code those. We want to do that all in symbols because that's how we put together our programs for the 68000 in the first place. Well, if we're going to have symbols set up that are shared, we need the linker to be able to resolve those symbols, and we also need to be able to evaluate those relocations at runtime. Now, what do I mean by evaluate relocations? That's the process carried out by loadseg in Amiga OS that loads programs into an area of memory. We're not going to know in advance where it is, and before running the program, loadseg looks at what has been loaded and works out all the different offsets to the various symbols that have been defined and fills in what the values are based on where it has loaded the program. It's a very clever bit of programming that, so that we don't have to worry about the fact that our program might end up running in any area of memory. But wait a minute, didn't I just say that loadseg sorts all that out? So what's the issue with relocations? Well, the issue is this, that the DSP3210 cannot load a full 32-bit value into an R register, an integer register, in one instruction. So here's an example. If you want to load that hex value 1, 2, 3, 4, 5, 6, 7, 8 into register R1, you've actually got to do it in two 16-bit parts, and it takes 2 instructions to do it, as you can see in the following line. So the top line loads the lowest 16 bits, and then the second line does a shift OR. That's what that double angles and the bar means, is a shifted OR in, and then it ORs in the top 16 bits to give us the full 32. The problem there is that we've split our symbol which in this case was the hex 1, 2, 3, 4, 5, 6, 7, 8 across two different instructions. And the Amiga hunk format doesn't support symbols and relocations split over two instructions like that. So we've immediately uncovered a problem here that we cannot use the Amiga hunk format in order to do our executable. In other words, we can't use conventional linkers that rely on Amiga hunk format, and moreover, LoadSeg can't evaluate those relocations. So what are we going to do? Well, part of the problem is also shared by PPC processors in the sense that they too cannot load 32-bit values in one instruction. So what the assembler does, ASM3210, is to produce an ELF object file, not an Amiga hunk object file. And ELF object files can accommodate the PPC style of symbols. So all ASM3210 does is pretends that it's producing a PowerPC object file with the particular type of relocation that we need. Additionally, VLink, which is part of the VBCC package, and the whole reason I was mentioning VBCC earlier, is that VLink can link PowerPC ELF object files with either Amiga hunk or ELF 68000 series object files. So that sorts out the linking through ASM3210 producing ELF files and using VLink. We've solved the first problem. However, we've still got the remaining issue that we've actually got to evaluate those symbols at runtime because LoadSeg isn't going to work on Amiga OS version 3 with ELF object files. So what's the solution to that? Well, another program I wrote called ELF to EXE M68K, which provides a wrapper to our final ELF object that's executable. And what that wrapper does is to be the first thing that is executed by LoadSeg, and the wrapper itself then goes and evaluates all the remaining symbols from the ELF object file at runtime. In effect, it takes over the relocation process that LoadSeg would otherwise do. The wrapper does instead on those ELF symbols. So we've solved both problems. And through using a combination of ASM3210 and ELF to EXE M68K, we can produce a single Amiga executable file, which is what our end users want. That all takes a bit of explaining. What I think we need to do is to actually look at a makefile and see this in action. So here is the makefile from Mandel DSP. I think though, before we go walking through what this does and how it works, let's just take a look through the source files and begin with Mandel M68K.c. So this does the bulk of the task on this CPU side. It interacts with the OS, sets up the screen, does keyboard control, colors the pixels based on the data that the DSP provides. This is all familiar Amiga OS C code. And perhaps the one thing to point out actually is here where the DSP labels in the DSP program are getting pulled through as external variables. And you can see you could just, the other 68000 series source file is DSP3210.c, and all that is doing is providing some functions to interact directly with the DSP, so to reset it, to interrupt it, etc. And actually, rather than go through all of this, perhaps the easiest thing to do is to look at the header file, which describes the functions that are available. So we can initialize the DSP, we can close down the DSP when we're finished, we can interrupt it every time we're ready for it to act on the next set of data. And then we've got a function to determine whether the DSP is busy or it is ready for the next round of data. So those are all 68000 series source files. Then we've got a few assembler source files for the DSP itself. So beginning on the left here with DSP3210 init, this is some code that just copies across the program into the onboard 8K of RAM space, the on-chip RAM, and then sets up a new interrupt vector table here and some very brief code to handle interrupts. So this is, if you like, a stub that is ready and waiting to have some source code added that will actually do the function of the program, so you can reuse this bit of code that is always there to initialize the DSP. The real task of doing Mandelbrots is in Mandelbrot.s here. Let's just go to the top, where here you can see declaring a lot of global variables that other bits of source code are going to pick up, and then one external symbol here for DSP flag, where that is going to be in the shared memory data so that the CPU can read the DSP flag and find out what the DSP is doing, and equally the DSP can update that. I'm not going to go through all of this source in any detail. It's there. All of these files are there on my GitHub page that I linked earlier, so you can go and have a look through all of this yourself. Perhaps the one thing to point out is this macro here, which allows the use of PC relative addressing very easily, and you can see it in use, in fact, in this line here, where I'm setting the register R5 to be an area of data lower down in this program, but using PC relative addressing, and therefore I can, if I work in that way, I can relocate all of this code to the on-chip RAM without any worries about upsetting absolute addresses. So this macro or something like it is really helpful in allowing PC relative addressing. Anyway, the .s files here are DSP files, the .c files are 68000 series C files. How does our makefile work? Well, what it's doing is putting into operation all the things I was talking about earlier. So let's begin. It's going to end up generating mandel dsp.exe as our ultimate file. But to begin with, in these lines here, all it's doing is compiling the 68000 series C source into object files. So because we're using the -c flag here, we're just compiling into object files. We're not compiling all the way into executables. Next, we are going to pull all of those together in this line here into something called M68K final as a final object file that just contains all the 68000 series object files. So we're using vlink, and we're ensuring that we are producing an ELF object file in 32-bit PPC style when we pull together all those object files, and we're going to link in various libraries at the end of it. That then completes all the 68000 series stuff. What we've got to do next is assemble the DSP source code, which is this set of lines here, where we're using ASM3210 to create ELF style object files from our assembly source in both cases. And then we link the whole lot together, which is happening here. So we're linking together where we ended up with our CPU object files and our two DSP object files, linking it all together still as an ELF 32 PowerPC object file and calling it mandel final. And then finally, we could use ELF to exe M68K to take that object file and convert it into an executable. So this is where that wrapper gets applied and it turns into an Amiga executable that's going to sort out all those relocations for us. So that's quite a lot to go through, but this basic formula is going to work in the majority of cases where you want to be able to mix CPU code with DSP code and use symbols between the two parts of it, provided that you're going to end up with an executable. Really, it takes all the stress out of that side of things, which is what the whole design of this was all about in the first place. So that's it. That's everything really you need to know to go ahead and program your own application that's going to utilize the DSP on the AA3000 and the Plus variant, and write your own programs. And I really wish other people would. Perhaps a place to start with all of that is to take the Mandelbrot code that's here in these source files and optimize it. That I certainly haven't made any attempts to do that, and a lot could be done to make it operate even faster than it currently does. So maybe that's a place to begin, just to get going with programming on the DSP. I'm certainly looking forward to seeing other people's programs for the DSP. It's been too long now since my programs were out there, and we do need some other ones. So there's the challenge. Let me leave you with that, and I'll see you again next time for more retro computing fun. Bye.